Okay, welcome back. Just an announcement to start. I guess technically Friday, the 3rd of July is supposed to be a university holiday. Even though we're not actually meeting, I guess I won't post a lecture that day. So there's 2 lectures this week. And problem set 2, which is due on Monday, will cover just material from what we talked about on Monday and what we're talking about today. Okay, so let me just remind you, last time, the last result we showed was that every spanning list can be reduced to a basis. The title of the slide was bases are not that special. They seem like a kind of special thing, but if you have any old spanning list, you can always extract a basis from it. And then we said that we would start today by proving sort of the corresponding result for linearly independent lists, which is if you start with any linearly independent list, right? Maybe it spans, maybe it doesn't. If it spans, you already have a basis. But if it doesn't span, you can take that linearly independent list, add some vectors, and obtain a basis. This says basically that you can start a basis with whichever linearly independent vectors you want. You don't need to start in some kind of special way. Okay, let's prove this. All right, so suppose that you have a linearly independent list. So U1, U2, through UM is a linearly independent list in a finite dimensional vector space V. Okay, well, one corollary of the last thing that we proved last time was that every finite dimensional vector space has a basis. So we know that V has a basis. So by the previous corollary, or if you're Canadian, corollary, V has a basis. And let's just say the basis is W1 up through Wn. Okay, now let's consider the list where you just take all of the U's, all of the W's. This list definitely spans because the W's by themselves span. Right, so this list spans V. And now we can again use the previous result. The previous result says if you have a spanning list, which is exactly what we have, from there you can extract a basis. Okay, but not only that, the technique in producing a basis from a spanning list is at each step, first step you look at the first vector. Basically, if it's linearly independent, you keep it. If not, you delete it. Then you look at the next vector. If it's linearly independent from, like when you add it to what you started with, you keep it, otherwise you delete it. Right, so this is a spanning set. It means that we can extract a basis from it. But if we run the algorithm from the previous proof, we'll never throw out any of the U's, because at each point, each UI is not in the span of the ones before it because the U's were supposed to be in linearly independent list. So if we run the algorithm, we'll get a basis, and we didn't throw out any of the U's, so we have a basis that starts with the U's, which is what we want. Right, so now run the algorithm. From the previous proposition. At the first m steps, since the U's are linearly independent, each uj is not in the span of all the ones before it. So we do not delete any U's. Hence, we're left with a basis that starts with the U's. We obtain a basis containing U1 through UM, and then some of the W's, which is exactly what we want to prove. Okay, so this result shows that you can start a basis however you want. It's always possible to, I mean, as long as you're starting with a linearly independent set, it's always possible to complete it to a basis. Okay, now the last result in this section is a result dealing with direct sums. And it's not particularly deep or anything, but I think it's probably worth doing the proof of just because I feel like we haven't talked that much about direct sums. I'll also put some problems on your problem sets about direct sums. They're an important construction in linear algebra. So suppose V is finite dimensional and that U is a subspace of V. Okay, what this theorem says, this proposition says, is that every subspace has a direct sum complement. In other words, V is our big vector space, U is a subspace sitting inside of it. We can write V as a direct sum of U plus something. So then there's a subspace W of V such that V is equal to the direct sum of U and W. Okay. How do we prove this result? Okay, well, first of all, since V is finite dimensional, one thing that we proved is that every subspace of a finite dimensional vector space is also finite dimensional. So by a previous result, U is finite dimensional. Right, and then we also proved that every finite dimensional vector space has a basis. So this means that U has a basis. Let's say it's U1 up through UM, as usual. Okay, well, now we know that we can extend this list to a basis for V. Right, so now use the previous, like the immediately previous proposition to extend to a basis of V. Say, right, so we start off with the U's and then we add W1 up through Wn. Okay, so this process, which right, I should mention that these W's aren't exactly the same thing as the W's here, because in this proposition, these W's, these formed a basis of V, and then we threw some of them out. So when I've written the W's here, it's like here it's like I've thrown out the ones I don't need, right? So now this whole thing is a basis of V. Now, how are we going to find this other subspace W? One place to look is maybe if you take this span of the W's, maybe that'll do the trick, right? So let W be the subspace consisting of the span of the W's, right? Which we know is a subspace. We want to show, we claim, oh gosh, my pen is, claim, oh gosh, my pen is malfunctioning. We claim that V is equal to U plus W. How do I fix this? Let me just click around a little bit. Okay. Well, how do you show this? Right? So we have a result that says enough to show that V is the sum of U and W, and U intersect W is 0. Right? This was like our direct sum recognition theorem from maybe even the first day. Okay, so first, let's show that V is equal to U plus W. So first, we show V is equal to U plus W. How do you show that a vector space is the sum of two subspaces? I need to prove that every vector in V can be written as the sum of something from U and something from W. Okay, so let's let little v be in the vector space V. I need to write it as something in U plus something in W. But this list here was a basis, which means it spans. Since, let's maybe this star, since star spans V, there exist scalars A1 up through AM, B1 up through Bn, such that V is equal to A1 U1 plus AM UM plus B1 W1 up through Bn Wm. Right? Every vector in V you can write as a linear combination of these things. But now, since U is a subspace, it's closed under linear combinations, this vector is in U. Similarly, this vector is in W, which means that V is definitely the sum of U and W. Right? So this implies that V is equal to U plus W. Now I want to show that it's direct. That means that I need to show that the intersection of these two subspaces is empty. So next, suppose V is in the intersection of U and W. I want to show that V is the zero vector. If I've done that, then I've shown that it's a direct sum. Okay, well, if V is in the intersection of U and W, it means that you can write it as an element of U and you can write it as an element of W, right? So here's the U's are a basis of U, so you can write V as a linear combination of just the U's. The W's are a basis of W, that means you can write V as a linear combination of just the W's, right? So then there exist scalars. Let me use different letters just to not be confusing. So V is C1U1 plus CMUM, and it's also D1W1 up through DNWN, right? Because it's in U and it's in W. Well, I would like to show that V is 0. One thing I can do is I can take these two things which are equal to each other and subtract. This means that 0 is equal to C1U1 up through CMUM minus D1W1 up through DNWN, right? Well, now, again, star is a basis, which means that star is a linearly independent list. And if you look at this last equation we wrote, this is a linear combination which equals 0, a linear combination of linearly independent vectors. So since star is linearly independent, this implies that all the C's and all of the D's are 0. Right? But what is V? V is C1U1 up through CMUM, and all the C's are 0. So altogether, this implies that V equals 0, which means the intersection is 0, which means that the sum is a direct sum. Okay, so this is, I mean, it's kind of a nice theorem because it helps you to construct a direct sum complement to any subspace, right? You just start with the basis of your subspace, then you add enough vectors until you span the whole thing, and then you make sure that those vectors are linearly independent. And what you're left with, the span of those, is like this direct sum complement, this W. Okay, so you'll have some problems on your problem set throughout the quarter dealing with direct sums because they're very important. So I want to make sure that I give it sufficient time in lecture. Okay, now this takes us to our next topic, the last topic in chapter 2, which is dimension. Okay, so we have not yet defined dimension. What have we defined? We defined finite dimensional. We said that a vector space is finite dimensional if it has a finite number of vectors which span. But we haven't defined what it means to have dimension 3 or dimension 4 or anything. Right? One thing that should, if we're going to have any useful definition of dimension, certainly f to the n should have dimension n, right? R2 should have dimension 2, R3 should have dimension 3. Otherwise, it's not really a good notion of dimension. All right, so it turns out that, maybe you remember this from Math 308, that a good way to define the dimension of a vector space is the number of vectors in a basis. Okay, but in order for you to make that definition, you need to know that every basis has the same number of vectors in it. Because if you had a vector space and had one basis with 5 vectors and one basis with 6 vectors, well, what is the dimension of that vector space? It's not a well-defined number. On the other hand, if every basis has the same number of vectors, then it makes sense to say, oh, well, the dimension of this thing is the number of vectors in a basis. Which basis? It doesn't matter. All the bases have the same number of vectors. Okay, so we want to define dimension of V as the number of vectors in a basis. That's kind of our goal, but we can't do this unless we know that every basis has the same number of vectors, right? Luckily, this is true. Okay, so here's the result. Any two bases of a finite dimensional vector space contain the same number of vectors. Okay, and the proof technique for this is actually really quite simple. So what's the technique? We're going to use this result that we prove that any linearly independent list, the size of any linearly independent list is less than or equal to the size of any spanning list. Right, so in your book, this is proposition 2.27. In the notes, it's number 37, but we'll just use it twice, right? So here's the proof. Let's let B1 and B2 be two bases of V. Okay, well, B1 is linearly independent because it's a basis. B2 spans V because it's a basis. So by this previous proposition, the size of B1 is less than or equal to the size of B2, right? So by, I'll call it proposition 37 because that's what it's called in the notes, the size of B1 is less than or equal to the size of B2 because B1 is linearly independent and B2 spans, right? But also, B2 is linearly independent and B1 spans, which means that they have the same size, right? Actually, really clean, simple proof. And this means that no matter which basis, if you take a basis and I take a basis of the same finite dimensional vector space, we might have chosen different bases, but those bases have the same number of vectors, which means that we are now, it's legal to make that the definition of dimension. So here's the definition. The dimension of a finite dimensional vector space. V is the length of any basis of V. And it's denoted dim of V. So like with any new definition, I suppose I owe you a ton of examples. Or at least like 3 examples. Here's the examples. Okay, so the standard basis, we should do a sanity check first, of Fn, right? That's E1 up through En, contains n vectors. Right, and by the previous proposition, actually, that means any basis of Fn contains n vectors, which means that the dimension of this vector space is n, which is definitely something that we wanted for dimension. Okay. Next example. We saw that the polynomials 1 up through ZVM is a basis of the polynomials of degree less than or equal to m, right? We saw that these span because every polynomial is a linear combination of these. And you can argue that they're linearly independent because any polynomial of degree m has at most m roots unless it's the 0 polynomial. So this is a basis. This contains m vectors. So the dimension of this vector space is m plus 1. Okay, let me give you kind of a tricky example, but sometimes you can learn a lot of stuff from tricky examples. Just a warning that the dimension of a vector space depends on the field. What do I mean? So you can consider C, right, the set of complex numbers. This thing is a vector space over C, right? It's just C1. Right, in which case it should be one-dimensional, right? So the dimension of C is 1, right? Because you can take any non-zero complex number and get a basis, right? So like 1 is a basis. Because if you scale by any complex number, you can get any complex number you want. Right? Of course, any other vector will also be a basis as long as it's not 0. Any other complex number other than 0. Okay, but also, this is a vector space. You can view it as a vector space over R. Right? I actually think that this is a problem in your problem set because this thing has basis 1i, right? Because every complex number you can think of as a real linear combination of the number 1 and the number I. And these two things are linearly independent over R, right? If you scale I by any real number, you're never going to get 1. They're not scalar multiples of one another. So in that sense, right, as a vector space over R, the dimension of C is 2. It's a two-dimensional vector space over R. Okay, so what I'm trying to point out here is that this notation is actually a little bit ambiguous, right? Because we don't want things like this sentence and this sentence are both true. It seems like a contradiction. Okay, so luckily for most of the time, we just work over F, and every vector space is over F. So most of the time, this isn't a big deal. So in this class, we just work over F as our field, and all vector spaces are over F. So there's no ambiguity, which is why I can make this definition as just, you just write dimension. But in general, in the future say, you might want to be very specific about what field you're talking about. So if you want to specify, you might say that the dimension, you use a subscript C here to say that the dimension as a C vector space is 1, but the dimension as an R vector space is 2. Right, so this is just a technical point, but I don't know, even technical points are worth saying. The field that you work over matters. Okay. So we have a definition of dimension. It's the number of vectors in any basis. The point is, though, that when you work with dimension, how should you intuitively think of dimension? Intuitively, you should think of it as a notion of the size of your vector space, right? Why did we need to define dimension to talk about the size? Because in general, vector spaces have infinitely many elements. Almost every vector space has infinitely many elements. If you take the 0 vector space, I guess only has one vector, but other than that, every vector space over R or C will have infinitely many elements. Also, if you work over finite fields, then vector spaces have finitely many elements, but you probably won't do that until you take abstract algebra 402 or whatever. So the point is that dimension is a notion of size. Of a vector space, right? Counting the number of vectors in a vector space is not a useful notion of size because then most vector spaces will have the same size, infinitely many elements. Turns out dimension is the nice notion of size that we need. Because of that, lots of things that we should suspect should be true for any notion of size will be true. The issue is just proving it. All right, so let me give you some examples. Basically the examples, I mean, these results for the rest of the lecture today will basically say, oh yeah, dimension is a notion of size. Here's the first one. Okay, so as always, suppose that B is a finite dimensional vector space. And U is a subspace of V. One thing that you expect for a notion of size is the following. Well, how should the dimension of U compare to the dimension of V? If U is a subspace, if it's measure size, U is sitting inside of V, you better hope the dimension of U is less than or equal to the dimension of V. Okay, so again, the proof uses some of the things that we've been learning in this class. So first of all, let me just remark that we only define dimension for finite dimensional vector spaces, right? And I haven't said that U is finite dimensional. So at first you might ask, okay, is dimension of U defined? But recall that we had this result that every subspace of a finite dimensional vector space is itself finite dimensional, which means that U is finite dimensional. So since U is a subspace of a finite dimensional vector space, it is also finite dimensional, which means that dimension of U makes sense. This is a number. Okay. So now, how do I prove that the dimension of U is less than or equal to the dimension of V? I need to know the definition. The definition is the number of vectors in a basis. Okay, well, let's suppose that B is a basis of U and C is a basis of V. In order to prove this result, it's enough to show that B has fewer vectors in it than C does. And so by the definition of dimension, it is enough to show that the size of B is less than or equal to the size of C. Well, do we have any result that will do this for us? Well, actually, we saw a result earlier in lecture that gave us something just like this, right? Where is it? Here. We have this result that any linearly independent list in a vector space has size less than or equal to any spanning list. Okay, well, B is a linearly independent set of vectors in U, but since U is a subset of V, it means that B is also a set of linearly independent vectors in V. And so B is linearly independent. And since U is a subspace of V, the vectors in B are also in V. They're in U, which means they're in V. So B is a linearly independent list in V. On the other hand, C spans V. So again, by the same proposition, this means that the size of B is less than or equal to the size of C, which is exactly what we wanted. Right, so this says that this notion of dimension behaves sanely in this particular way. Okay. What's the next result in your textbook? The next result in your textbook says, again, that you should think of the dimension of a vector space as like a very good notion of the size in the following sort of technical way. So let's suppose B is finite dimensional. What it says is that every linearly independent list of vectors in V with length dimension of V is a basis. Okay, so why is this something that you might expect, right? So somehow the dimension, let's say the dimension of V is 5, right? Somehow this means that V is, the size of V is like, it's 5 big, right? In some way. Now suppose you have 5 linearly independent vectors in V, and you don't know that they span. You just know that you have 5 linearly independent vectors. Well, if the size of V is 5, there's like only 5 directions in V, and you have vectors that are pointing in 5 different directions, it seems like this means that they should already point in every direction, right? If you have enough linearly independent vectors up to the size of the space, then they should already span, because this dimension is capturing the notion of the size of the vector space really carefully. That's exactly what this proposition says. If you have 5 linearly independent vectors in a space of dimension 5, you know that they already span, and therefore they're a basis. Okay, and it turns out that the proof is actually very short, just a few sentences. So this will follow from the theorem that every linearly independent list can be extended to a basis. Right? So again, if you have a space of dimension 5 and you have 5 linearly independent vectors, you have a theorem that says, oh, well, you can add some vectors to the list to get a basis. But you also have a theorem that says that every basis has 5 vectors in it. Right? So if you added any vectors, you wouldn't get a basis, which must mean that you already had a basis to start. At some point, you're going to get a basis, but you can't have a basis with 6 or 7 or 8 or 9 or 10 elements. You must have started with a basis. Right? So if dimension of V is n, and V1 up through Vn are linearly independent, by that theorem, the list can be extended to a basis. This is the first thing we proved today. However, every basis of V has length n. So this means that V1 up through Vn must already be a basis. Because if we added any vectors, it wouldn't be length n. Okay, now every time you prove some theorem about linear independence, you should wonder, well, what if I come at it from the other side, the spanning side? Right? So what if I had 5 vectors that spanned a 5-dimensional space? Well, 5 vectors, they're living in a space with only 5 directions, and they're pointing in they're pointing in every direction in the space. But if there's 5 directions and 5 vectors are pointing in 5 directions, it seems like they should all be pointing in different directions. Right? So also, if you have exactly the correct number of vectors and they span, they must already be linearly independent, therefore they must already be a basis. That's the next proposition. Right? So these things sort of go hand in hand. Suppose V is finite dimensional, then every spanning list of vectors in V with length dimension of V is a basis. Okay, and the proof is exactly the counterpart of the proof of the previous fact. Right? Every spanning list can be cut down to a basis. That's the last thing we proved on Monday. Every spanning list can be cut down to a basis. So suppose you have n vectors which span. Well, from there you must be able to pick out some vectors and get a basis. But every basis has to contain exactly n vectors. So that means you can't actually take anything out. You must have started with the basis already. Okay, so it turns out that these two results, right, they're kind of nice because to show that something is a basis, by definition, you would need to check two things. You need to check linear independence and spanning. But if you know the dimension of the space, then this theorem says you only need to check one thing. If you have 5 vectors which are linearly independent in a space of dimension 5, you're done. Okay, so your book gives a nice example. So I'm just going to literally just copy the example from your book, but it's nice if we can go through it together. We can try to understand it a little bit. Let's let U be the set of polynomials in P3 of R such that their derivative at 5 equals 0. Okay, so this is a proper subset of P3 of R, right? Because some polynomials will satisfy this property. The derivative at 5 is 0. Some polynomials won't. So you will get some polynomials here in here. You won't get some other ones, right? So for example, let's see if I can do this. The polynomial z squared, let's say 1/2 z squared minus 5z. Gosh, you shouldn't try to come up with polynomials like this off the top of your head. All right, so this polynomial is in U, right? If we call this polynomial P, because P prime of z, that's z minus 5. And so P prime evaluated at 5, you get 0. Right, so this P of z is in U. But if we try some other polynomial, just like, I don't know, z squared, then the derivative is 2z, which means that Q prime of 5 is 10. And so that's a polynomial that's not in this subset. So this is a proper subset of the polynomials of degree at most 3. Okay, so one thing that you should ask is this a subspace? So in fact, U is a subspace. Okay, so why? Well, you need to check 3 things. You need to check that 0 is in there, the sum of two vectors in there is also in there, and the scalar multiple vector in there is in there. Right, well, the 0 polynomial, if you take its derivative, you get the 0 polynomial. If you evaluate at 5, you get 0. Right, so the 0 polynomial is in there. If P and Q are both in U, it means that P prime of 5 is 0 and Q prime of 5 is 0. Well, you can look at the new polynomial P plus Q. That's a new polynomial. And in calculus, you learned that the derivative of sum is the sum of the derivatives. So if you evaluate the derivative of this sum at 5, you get P prime evaluated at 5 plus Q prime evaluated at 5. You get 0. Right, so this polynomial is also in U. Yeah, which shows that U is closed under sums. And then finally, if you take any scalar alpha in R and you consider polynomial alpha P, this is again a new polynomial, you've scaled it. But you learned in calculus that if you multiply a function by a scalar and take its derivative, it's the same thing as multiplying the derivative by a scalar. Right? You can pull scalars out of differentiation. Which means that if you look at this new polynomial, alpha P, and you evaluate it at 5, it's the same thing as alpha times P prime evaluated at 5, which is alpha times 0, which is 0. So this polynomial alpha P also satisfies this property of having its derivative vanish at 5. So this shows that U is a subspace. Okay, then we could talk about, well, what is a basis of this subspace? That's really the point of the example. What is the basis of U? Okay, so here's the claim. The constant polynomial 1, the polynomial z minus 5 squared, and the polynomial z minus 5 cubed are a basis of U. Yeah, I don't think it's that obvious. I mean, in order to come up with a basis like this, you probably need to play around a little bit, but then you need some argument that you've actually found a basis. Okay, so first of all, you should check that these polynomials are actually in U. In other words, you need to check that when you differentiate them and you evaluate them at 5, they vanish. Okay, so just as an example, right, certainly if you differentiate 1, you get 0. But if you differentiate, I don't know, z minus 5 cubed, you get 3z minus 5 squared, I think, by the chain rule. And when you evaluate that at 5, you do get 0. So this thing, you can check that all 3 of these polynomials are actually in U. Okay. Now, how do I plan on using the previous theorem? The point is that we know that this vector space, the big one, we know that this one has dimension 4. Okay, also, we know that U is a subspace that isn't all of P3 of R. It's a strict subspace, right? Which means that the biggest dimension that you could have would be 3, right? Because it's not all of P3 of R, which has dimension 4, so it's slightly smaller. So it must have dimension at most 3. So if you can just prove that these 3 vectors, these 3 polynomials, are linearly independent, well, that's 3 linearly independent vectors in a subspace that can have dimension at most 3, which means that if you have 3 linearly independent vectors, it means that you have dimension at least 3, which means the dimension is 3, and so it's a basis. Okay, so it's enough to show that these vectors, these 3 polynomials, are linearly independent. Because this would mean that the dimension of U is at least 3, because you have 3 linearly independent vectors. But also we know that the dimension of U is at most 3, which together would mean that the dimension of U is 3, and then 3 linearly independent vectors form a basis. Right, so I've included a bunch of argument here. I haven't written it down, but you should follow the argument. Right? Okay, but then it turns out that showing that these vectors are linearly independent is not so difficult. So to show this, let's suppose we have a linear combination which equals 0. So suppose a times 1 plus b times z minus 5 squared plus c times z minus 5 cubed is the 0 vector, which is the 0 polynomial. What do I need to show? I need to show that the constants must be 0. Well, why are the constants 0? Let's look at the left-hand side here. And let's look at the coefficient on z cubed. What is the coefficient on z cubed if you expanded everything? The coefficient on z cubed is c. And so here the coefficient on z cubed is c. But on this side, the coefficient on z cubed is 0. And that means that c equals 0. Right? So c is 0, that means you cross this term out. Then you again look at the coefficient of z squared on the left-hand side. Well, the coefficient on z squared is b. On the right-hand side, the coefficient on z squared is 0. That means that b equals 0. And now you just have a equals 0. That means a equals 0. So by examining coefficients, you'll get that these 3 coefficients are 0, which means that the vectors you started with were linearly independent. The only linear combination equaling 0 is a trivial linear combination. So here's 3 linearly independent vectors in a subspace of dimension at most 3. That means that they're a basis. Okay, so there's a lot of stuff going on in this example, and I know that this vector space of polynomials is like not necessarily something that you saw in 308, but will be a good example to work through whenever you have any statement about abstract vector spaces, because this is an example that's different than f to the n, right? The kind of stuff that you're used to. So hopefully this at least give you one worked example. You will, of course, have lots of problems in your problem sets, etc., dealing with these things. So I thought it was worth talking through this entire example with you guys. Okay, the last result that we'll talk about, the last result in this section, in this chapter, is the following sort of very useful results. If U1 and U2 are both subspaces of a finite dimensional vector space, meaning that they are also finite dimensional, then the dimension of the sum, how does the dimension of the sum work? It's the dimension of U1 plus the dimension of U2 minus the dimension of the intersection. Okay, so the proof is in your book. I'm not gonna prove it for you. Let me just talk about 2 points. Okay, so one is that this is actually another thing that you would expect if you expect that dimension is somehow measuring size, right? Why is this? By analogy, if you have two sets, U and V, maybe I'll call them something, let's call them A and B, and you take their union, you can ask what the size of the union, right? Well, what is the size of the union, right? You have A here, that's horrible. You have A here, you have B here. How do you count the size of the union? Well, what you do is you take the size of A, then you take the size of B, but you've overcounted in the middle here, right? So you subtract off the intersection. This is a really horrific diagram, but this is called the inclusion-exclusion principle. Hopefully you learned it in Math 300. If you didn't, I actually don't remember. So I taught some of you Math 300. We must have covered this. Yeah, we definitely covered this. If you don't remember, that's not my fault if you took it with me. Nothing is my fault, actually. If you ever don't remember anything, it's not my fault. Anyway, so if you have sets, the size of the union is equal to the size of the two sets together, subtract off the size of the intersection. Right? That's sort of exactly what this is saying, except with sums of vector spaces instead of unions of sets. Right? How do you determine the size of this sum? Well, it's the size of each of them minus the size of where they intersect. So if dimension is a notion of size, then this is the kind of thing that you would expect when you're measuring the size of a sum. Right? You put two things together, you add their sizes, but you subtract off where they overlapped. Okay, another corollary of this fact is that the dimension now of a direct sum, right? Well, that's just the sum, right? So it's this thing. That's exactly what it is. However, if it's a direct sum, then U1 intersect U2 is just 0, which has dimension 0, right? So this whole thing is just the number 0. So this is just the dimension of U1 plus the dimension of U2. Right, so a direct sum is like they intersect in as small an area as possible. You're sort of, there's no overlap between, except every subspace intersects in the 0 vector. So somehow that's the meaning of a direct sum. It means that you can write every vector as something in U1 and something in U2, and there's no ambiguity because they don't intersect anywhere. In other words, you can write it uniquely as something in U1 plus something in U2, which is another characterization of the direct sum. Okay, so I encourage you to read the proof in your book. It's like a little bit technical. It's not so important. I think it's more important to know the results, but you should be able to follow the proof in your book. All right, so like I said, no lecture. I won't post a lecture on Friday. You still have a homework set due on Monday. And on Monday, we'll start talking about chapter 3.